Hello and welcome back. So let us try to understand ridge regularization and then try to apply this onto a data set and see how it works and how to play with the regularization parameter or shrinkage parameter we call it as, because we are trying to shrink some of the coefficients by playing with that shrinkage parameter. So if you look at the equation, right, the cost functions equation, we added a little more weight to the cost function. This is also called as Tikhonov regularization, right? So the MSE, mean squared error. What is mean squared error? Y cap minus y whole square sigma I is equal to 1 to m divided by m is the mean squared error. That's the cost function. Original cost function was that. And then we added an additional regularization term, lambda divided by m into 1 by 2 sigma I is equal to 1 to n theta I square. Theta 0 need not be regularized. The intercept need not be regularized. The other theta should be regularized because the importance of the features, the theta 0 is an intercept. The coefficients of x's and x squares, x cubes, interaction terms are the ones we try to regularize and reduce or increase the model's complexity, right? So this additional term when you add it, and that is also in terms of weightage, what the algorithm will try to do is it will try to reduce the cost. Right? Our gradient descent algorithm's main motto is to minimize the cost. We have added additional weight here. It will definitely try to minimize. When it is trying to minimize, it will try to minimize the thetas. It will try to reduce thetas a little bit, so that the weight reduces. When it reduces thetas a little bit, the coefficients associated with the features will reduce. When the coefficients associated with features reduce, the curve becomes a little smoother. If the curve is like that, when you reduce the thetas, it will become smoother. Right? So that way, the model will actually become little less complex. The model is too complex because of the higher degree polynomials and interaction terms coefficients are high. When you add an additional weight to the cost function, the objective of the algorithm is to reduce the cost. So it is going to reduce the additional cost. Additional cost is in terms of theta, and it will try to reduce those thetas to reduce the additional cost. In turn, it will help you smoothen the curve. The coefficients of the x's are theta, so when thetas reduce, the importance of those features will reduce and the curve becomes smoother. When curve becomes smoother, there is a possibility that it fits well on the train set as well as test set. The model is not working well on the test set because it overfitted and ignored the generalization. When you make the curve a little smoother, it actually works well. That's the analogy behind how it works. Okay, so here the lambda is called as the regularization or shrinkage parameter. If you put this lambda as 0, the cost function becomes the original cost function, j is equal to msc. That means the overfitted model will stay as overfitted model. If you put this a number close to 1, then it will become like very soft. The complex curve becomes very smooth. When you put 1 here, what are you doing? You are adding lot of weight. When you put 0, no weight. When you add no additional weight, it is going to be the same, right? The same overfitted model. And when you add 1, a number close to 1, then it's going to become big, right? Then it will try to reduce the thetas, and that way the model becomes too smooth. So if the number is close to 0, the lambda is close to the 0, then the model will stay close to whatever overfitted model we have seen or we are trying to fine tune. If the lambda is close to 1, it will try to make the model as biased as possible, right? If you put the lambda close to 0, the model will be overfitted or high variance model. If you give a number lambda close to 1, the model will be high biased model. You need to play with this lambda and find the best model which fits well on the train set and test set both. Okay, so the lambda is the key. This is called as shrinkage parameter. This is one of the hyperparameters. When model overfits, then only you need to play with this. The learning rate is to converge faster. The regularization parameter is to make the model best fit on train set and test set. To cure the overfitting or to reduce the complexity in the model, you will use the regularization parameter. This whole thing is called as regularization term. Okay, so how it is exactly working? As a layman's in layman's terminology I explained so far. Let us see the math equation and try to understand how it's working. So if you look at this this equation, right? This is actually the derivative. This is when you add this additional term, the derivative becomes like this: theta is equal to theta minus alpha into, this is the original derivative term, and additionally this term gets added, right? To theta, we are subtracting some value with normal gradient descent or stochastic gradient descent, but after adding regularization term, we are reducing even more. Okay, that is also a layman's terminology kind of general explanation. But if you take this theta j common from this equation, right, what happens is 1 minus alpha into lambda by m. It becomes alpha is the learning rate, which is a small number, maybe 0.01 or 0.001, or in our visual example we have shown 0.0005. Right? It's a small number. And then lambda is also going to be a small number, a number between 0 and 1. When you multiply these two small numbers, it gives you even smaller number, and we are trying to divide it with the m, number of records. Number of records must be at least 1000 minimum, right? 1000 is not a good data set. Maybe 10,000, maybe 100,000, right? It's going to make this numerator, whatever the numerator result, even smaller. You are subtracting it from 1, that means it's going to be 0.99999 something, and you are multiplying that with theta. When you did not apply regularization, you are just subtracting this normal slope term by multiplying with alpha from the theta. But when you applied regularization, you are multiplying this theta with a small number, right? 0.999 number. That means it shrinks a little bit, and then you are reducing the normal term. That means the reduction is going to be more when you apply the regularization than the general normal gradient descent or the stochastic gradient descent. When you apply regularization, it affects the theta. It reduces theta. Depending on lambda's value, it reduces. If the lambda's value is big, the reduction is going to be huge. If the lambda's value is small, the reduction is going to be small. If the lambda value is small, reduction is small, that means the model will stay where it is. That means the model is already overfitted. That's where you are trying to apply regularization. So model is overfitted. You chose a lambda which is small, so it is going to stay there only. If you want to reduce even more, complexity, you need to increase lambda. When you increase lambda, complexity reduces, overfitting reduces. When decrease lambda, complexity increases, the overfitting increases. So when you increase lambda, the model goes into bias, high bias model. When you decrease lambda, it goes into high variance model. That is theory and theoretical understanding about regularization. In the next session, we will look at a code example and play with lambda and make a overfitted model, best fit model. Thank you.